From the previous video, we know qualitatively what to expect when we connect this charged capacitor to a resistor. We know that we have some energy stored in the capacitor, and over time that's going to be transferred to the resistor. So what we want to do here is we want to take a closer look at that quantitatively. Specifically, what we want to do is we want to find an expression for our capacitor voltage V sub C as a function of time. So we can start by noticing that once we close that switch, we're going to have current flowing in this direction. So as it's drawn, it's going to be flowing clockwise, and that's going to result in some voltage drop indicated by this blue plus and minus across our resistance. We can apply our KCL at any point in the circuit. So let's say we focus on this point at the top, again, more or less arbitrarily. So we have some current flowing in from the left and flowing out of the right. We know that current in has to equal current out. So we can say that we have some capacitor current I sub C is equal to some resistor current I sub R. Both of these are functions of time. As we see, they're going to be changing. We'll see that more clearly a little bit later. So now what we need to do is we can go back to our IV equations for each of these components. One key thing to note is we do still need to keep in mind our passive sign convention. So on the left, because our current is going from negative to positive in our capacitor reference voltage, we need to include a negative sign in our IV equation. So again, a capacitor is a passive component, just like a resistor, so we do need to keep in mind our passive sign convention. We know that our capacitor current is equal to C dV dt, so that's what I have here, again with that negative sign out front. Our resistor is much simpler. We just have our current is V over R, where we know that the voltage across the resistor is the same as the voltage across the capacitor. And for our resistor, our current is going through a voltage drop from plus to minus, so we do not need the negative sign there. So from here, I can just rearrange this a little bit. So I can move this negative term over to the right, or we could think about it as moving this term over to the left and then getting rid of the negative, multiplying by -1. And we can do that because we would have then 0 on the right. Either way, we end up with this first order differential equation. More specifically, this is a first order ordinary linear differential equation with constant coefficients. And so that's nice because, as we're going to see in the following slides, that's a relatively easy equation to solve for. So hopefully you've had practice with that in your differential equations classes. So if we take a closer look at that, here is the general form of our solution. Based on this equation, we know our voltage for our capacitor has to have the form of some constant times an exponential. So all we need to do to find the specific solution is figure out what these constant values are, K and S. And then of course T is just our variable in time. So I'm going to plug this general solution back into my differential equation from the previous slide. And so doing that, so in the brackets here, I've taken the derivative of our general solution. So of course, the derivative of an exponential is just the exponential itself, but then we have to do chain rule on the argument of the exponential. So because of that, we get an S coming down, and then we also have the K, a constant multiplied by that original expression, which is still there. And then of course, we just have our V sub C of T. So I can play around with this a little bit. What I'm going to do is move this second term over to the right side, factor out that, pull that S out of the brackets. Here is all I've done there. And what we see then is that these terms in brackets are the same. So I can divide through, and I can say then that RCS is equal to -1. In an actual circuit, we would know the R value, we would know the C value, or maybe that's what we're designing for, and we know the S. But let's say we know R and we know C. So we want to solve for this constant S. So now we can say that S is equal to -1 over RC. And again, if R and C are known, then we'll know a specific numerical value for this S constant. And we'll come back and we'll talk about what that means more broadly here in a little bit. So if we come back to our equation now, we've got VC of t is equal to K e to the -t over RC. So we know it's a decaying exponential, and we know that the shape will look something like this. So recall we had a initial voltage applied to our capacitor, and then we have some decaying exponential over time once we close that switch at t equals 0. So now we just need to figure out what that constant k is. It's worth noting, recall that our capacitor voltage needs to be constant. So we said for our capacitor, we have I equals C dV dt. So C dV dt. And so the reason our capacitor voltage has to be continuous is that if we have an incontinuous voltage, that's essentially some number for our change in voltage divided by 0, right? So if it's changing instantly, there's some change in 0 time. Something over 0 is infinite, so then we would get some infinite current. So because of that, we do need our capacitor voltage to be continuous at this point right here. So I can write that mathematically by saying our capacitor voltage at 0 minus, so the minus indicates we're approaching 0 from the left, has to be equal to the voltage as we approach 0 from the right, or VC0 plus. So again, this is just some mathematical notation indicating we're either right before the switching event or right after the switching event. But because we know the capacitor voltage has to be continuous, we can say that both of those are equal to our initial capacitor voltage, which again was the voltage over here on the left side. So we can use that information to then figure out what our constant value k is. So here's our partially solved general expression. We know for t equals 0 plus, the capacitor voltage is that initial voltage. The reason we want to look at 0 plus is this equation is valid for our 0 plus. That's when we were solving it for. So if I evaluate at t equals 0 plus, well, when we do e to the 0 plus 0 minus, it really doesn't matter if it's 0 plus or 0 minus, but we know that anything, including e raised to the 0, is just going to be 1. So we end up with our k is equal to V sub I, so that initial capacitor voltage. So we have both of our constants, our k and our s, so we can plug those into that general form of our expression. And so now we get this equation. So we have our capacitor voltage, Vc of t, is equal to Vi times e to the minus t over tau. And so I've defined this new term here, tau, which is our time constant. We'll talk about that a little more in the next video. But this time constant for this particular circuit is equal to RC. So again, we can confirm that this equation matches the plot for our capacitor voltage versus time that we saw on the previous slide. Note that I don't have this equation in a solid box. The main reason for that is that this equation is specific to the circuit that was shown at the start of the video. Later on, I'm going to give a more general equation that I believe is easier to use. You don't have to sort of readjust the circuit to fit a particular form.